Denis, thank you for the flexibility.
Yes. Okay, thank you very much. So the title of this says liquid metal droplets, and to be clear, these are molten metal as opposed to nanoparticles in liquid. And I would be remiss if I didn't acknowledge Manoj, who actually did the work. I signed the checks for everything, but the students do the work. So let's go ahead and get started here. So as background, the process that I'll talk about here is very different from everything else we do. So we do most of the same digital processes that many of you do, aerosol jet, dispensing, inkjet, photonic sintering. We do all of that on a daily basis. The process that I'll show you is not really well suited to replace any of these processes. It's an and instead of an or, okay? So here's how the process works. We're melting metal in a tiny little crucible that's about the size of your pinky. You're feeding wire as the feedstock material. So this is very low cost feedstock material. You can buy any wire that you like. It's melted, and then it uses magneto-hydrodynamic jetting, which if you're a physicist, that means something to you. All you need to know is that we're able to eject droplets on demand of molten metal. Now, this was originally developed as a metal additive manufacturing or a metal 3D printing process for making aerospace parts and things like that. And that's my background. But we also, as you saw in the previous slide, we do a lot of printed electronics as well. And so in my brain, I started thinking, hey, it would be kind of interesting to try printing metal traces with this process where we're not curing or sintering nanoparticles. We're instead directly printing molten metal traces, or well, solid metal traces after they've solidified. So, you know, what you're seeing in this video here is a 3D part being printed, but you can see those droplets landing. Of course, once they hit the substrate, they cool down and solidify. All right, and we'll go into a little bit more depth here. So the system was originally developed. It was a father-son startup company who I met in the basement of their house in 2014, building the initial prototype. They were, and I helped them get going. They were then acquired by Xerox in 2019. And so we had the very first Vader Systems machine. They have nothing to do with Star Wars. That's the family name, Scott and Zach Vader. So we had the first machine there in 2017. Then in 2021, Xerox came out with their upgraded version of that machine. Again, it was designed to do 3D printed metal parts. We're adapting it for printed electronics here. So you can see in the bottom bullets there, the nozzle diameters. This is fairly big world kind of stuff. These are not 30 micron traces. These are large diameter traces, and you'll see micrographs. So let's go ahead and get into some of the details. So the practical costs or the practical considerations. The cost was one of the big things that drew me to it. Was I have dollars per pound there. A kilogram roll of copper wire is 30 to 35 US dollars. So you can imagine a kilogram of nanoparticle ink would be quite a bit more than 35 US dollars. So that's very appealing. There's no drying, curing, the cleaning afterwards, and so on. And the performance is the big one, the electrical performance, where we are printing what functionally is solid core metal wires, and we're getting the same conductivity as the bulk material. Okay. Now, I'm not selling machine, I'm an academic, so I'm also going to talk about the negatives here. The feature size, as I said, the smallest nozzles that we have jetted with are 150 microns. There's nothing limiting going to smaller diameter nozzles. It just takes more energy to push the fluid through a smaller diameter nozzle. So this machine that we're working with We can jet from 150 microns. We have not successfully